evening all. So, so today we are going to discuss about previous gate question papers and what are the routes they are asked. Okay. So first of all, different to the gate bits and the previous question papers. So first of all, we will discuss about what is the remaining part. Okay, that means coming to here. So we are having the next part of the fluid mechanics is nothing but fluid kinematics and fluid dynamics. Okay. So while coming to the fluid kinematics, so the fluid kinematics is also one of the type of study of fluid in the motion where the pressure and pressure forces are not considered. Okay, that means the movement of the fluid should be without considering the forces. Okay, so the fluid need to be in the rest position. Okay, we need to find out the forces when the fluid is in moving condition. That means from the rest position to it needs to move. Okay, so the fluid needs to move from the rest position means we need to apply little bit pressure or so the surface should be inclined. Okay, so based on those conditions here, so we are taking this to these considerations. Okay, so while coming to the fluid kinematics, so in the fluid kinematics, so this is a study of forces where the fluid is in motion, where the pressure and the pressure forces are not considered. Okay, so while coming to the fluid mechanics here, so we'll study about flow patterns, that is types of flows and flow patterns. Okay, so while coming to the flow patterns, here we are having streamline, path line, streak lines, and stream tube. Okay, so depends upon these flow patterns. So we are having the different types of classifications of flows. That is steady flow, uniform flow, non-uniform flow, laminar, turbulent, rotational, irrotational. Okay, that is in one-dimensional, two-dimensional, and three-dimensional flows are there. Okay, so while coming to the fluid dynamics, okay, so the study of fluids in the motion where pressure forces are considered. Okay, that means while coming to the fluid dynamics, so we are finding the forces in the fluid when the pressure and pressure forces are considered. Okay, that means so we are finding the forces in the fluid when the fluid is in motion by considering external pressure and pressure forces. Okay, so with the help of the fluid dynamics, so here we can find out Euler's equations, Bernoulli's equations, and practical applications of the Bernoulli's equations. Okay, here we also get that momentum equation. So and forces acting in a momentum equation also. Okay, so first of all, so see here. So here we are having different types of flow patterns. Those flow patterns are streamline, path line, streak lines, and the stream tube. So I'll come into the fluid dynamics. So first of all, we are finding the surface forces, body forces, Lagrangian method, Eulerian method, and Euler's equations and Bernoulli's equations. Okay, so listen carefully. So here we have steady and unsteady flows. Okay, so when we are telling that the steady flow means a flow is said to be steady flow when the properties of the fluid does not change with respect to the time. Okay, that means we are having different properties. Okay, so just like the mass density, weight density, specific gravity, so vapor pressure, temperature, like this. So we are having number of properties. Okay, so all the properties. So for example, if we need to take any one of the fluid, okay, the fluid contains some properties. Okay, so the properties should not interchange with respect to the time. Okay, then the flow is known as steady flow. Okay, that is so density with respect to the time, pressure with respect to the time, or temperature with respect to the time, like this. Okay, so if it is unsteady flow means any one of the property of the fluid, any one, not all, or either it should be taken by all. Okay, any one or all. Okay, so just like velocity, okay, so viscosity, temperature, any one of the property of the fluid is equals to 0 with respect to the time, okay, or if it changes with respect to the time, then the flow is known as unsteady flow. Okay, in the same way, here we have uniform flow and non-uniform. Okay, a flow is said to be uniform if the if the properties of the fluid and flow do not change. So throughout the consideration of the sections, okay, then the flow is constant. Okay, such type of flow is known as uniform flow. Okay, that means so throughout the section, so throughout the chamber, so whatever we are having there, okay, so throughout the section, so it should be constant. Okay, that is the dp by dx equals to 0. Okay, so while coming to the non-uniform flow, throughout the length it may be changes. Okay, that is dp by dx not equals to 0. Okay, so very small changes is there. Okay, so while coming here we have a streamline, path line, straight lines, and stream tubes. Okay, so observe clearly. So here we have the streamlines. Okay, the streamlines are nothing but imaginary lines. Okay, so for example, for streamlines, so it is used with respect to the point of contact, and so we are introducing stream tubes also. Okay, the stream tubes is also an imaginary tube, and the streamlines is also an imaginary lines. Okay, well, coming to the stream tube, so it removes the tangential portion of the velocity. Okay, so while coming to the straight lines, so point to point concentration will be added here. Okay, so just like this. So these are the flow patterns. Okay, so please concentrate on the figure. Okay, then so these are the dimensions of the units. Okay, so dimensions we have mass, length, time, and temperatures, and we have the symbols as m, l, t, theta. So for mass it is m, for length it is l, for time it is t, for temperature. So here we are having so t theta. Okay, so well, coming here we are having that units, that is having kilograms, meter, second, and kelvins. Okay, so and here we are having the derived units, velocity, acceleration, and forces. Okay, so well, coming here we are having L into t power minus 1, then acceleration as L into t power minus 2. While coming to force, we are having m L t minus 2. Okay, and while coming to the SI units, so we have the derived units. So velocity, so regular units are mass per second. Okay, and acceleration is mass per second square, and force equals to newtons. Okay, so here we have is the pressure stresses. So that is, so we have the pressure stresses density, specific weight, relative density, viscosity, energy, and power. Okay, so as usual, here we are taking the gravitational forces value as, so the acceleration due to gravitational forces is 9.81 meter per second square. Okay, so listen carefully. So here we are having the quantities as length, mass, time, temperature, and forces, and we have the SI units, that is meters, kilogram, seconds, Celsius, and of course newtons, which is nothing but kg into meter per second square. Okay, so please see here. So here we are having rotational and irrotational flows. Okay, when the flow is said to be irrotational, if the fluid elements does not rotate about their own axis, okay, as they move along the flow, and is rotational if the fluid elements rotate along their axis as they move along the flow of the directions. Okay, so while coming to this one, so rotational flow means so it needs to rotate about their own axis. Okay, so while coming to the irrotational flows, it does not rotate about their own axis. Okay, so based on this, we are having some bits. Okay, at the same time, so here we are having the continuity equation formula. So that is Q equals to A1 V1 equals to A2 V2. Okay, so Q equals to, so A1 V1 equals to A2 V2. Okay, so here we are having the continuity equations. Okay, that is Q equals to A1 V1 equals to A2 V2. Okay, so with the help of this, so we are finding the discharge formula. Okay, so here also we are having the same. So this is a 3 dimension. And so before one is the one dimensional force, and here also we are having the same, that is, so Q equals to A1 V1. So or while coming to this terms, so we are having that, so du by dx plus dv by dy plus dw by dz equals to 0. Okay, so this is for 3 dimension. While coming to the 2 dimension, that is du by dx plus dv by dy, or dv by dy plus dw by dz, or dw by dz plus du by dx equals to 0. Okay, like this. So while coming to the 1 dimension, we are having the du by dx equals to 0, then dv by dy equals to 0, then dw by dz equals to 0. So here we are having that u, v double as the velocity components. Okay. So now I'll come to the momentum equation. So this is also one of the major part, that is completely depends on force equals to mass into acceleration. Okay. So F equals to m into a. So F is nothing but, so we are having different types of forces, the gravitational forces, pressure forces, and so on. Okay. That is summation of all forces equals to mass into acceleration. Okay. Then acceleration is nothing but, so we are taking the as dt because start interval of time. Okay. So because acceleration we are taking as meter per second square. Okay. That is dv by dt, which is nothing but v into dv by dt. Okay. So it should be like this. Okay. So force equals mass into acceleration, and m equals to du by dt, which is nothing but d into mu by d. Okay. So like this, they are considered. So I'll come into the fluid dynamics. So here we have different types of forces, because here we are considered, because in the fluid dynamics we are considering the forces when the fluid is in the movement condition. So that forces is nothing but either it may be a pressure forces, or it may be a gravitational forces, or it may be a viscous forces, or turbulent forces, or surface tension forces, or compressibility forces, or whatever it may be. Okay. So listen. So here we have the summation of all forces equals to mass into acceleration. That is, so ma. So generally the forces acting in x-axis direction, that is Fx equals to m into a. That is forces in the direction of x-axis equals to mass into acceleration. Well, coming here we have gravitational forces plus pressure forces plus viscous forces plus temperature forces plus surface tension forces plus remaining forces equals to mass into acceleration. Okay. So like this, if we neglect any one of the forces, so automatically we will get the some equations. For example, so if we need to get to find out Euler's equation, okay, so we need to get that, so force equals to mass into acceleration. That is, while getting for Euler's equation, we are considering only gravitational forces and pressure forces. That is, Fg plus Fp equals to ma. Okay, like this. If we want to find out the Navier-Stokes equation, so we need to eliminate Fs and Fp. Okay, with the help of this, we will get the Navier-Stokes equation. Like this, so we need to eliminate any one of the forces. Okay, and we will get so one equations. Okay. So for example, if we need to get the Reynolds number, so we need to find out that, so Reynolds number equals to initial forces divided by viscous forces. Okay. So if we need to get the Prod number or Prod equation, so we need to find out that, so inertial forces with respect to gravitational forces. Like, okay. So with the help of this one, so we'll find out the Bernoulli's equation and the formula. That is, here we are having, so dp by rho plus vd plus dz equals 0. Okay, which is nothing but the Euler's equation. If you go through with this one, so if you add the integral, so we'll get the Bernoulli's equation. Okay, so the dependence upon the Bernoulli's equation is nothing but law of conservation of energy. Okay, the basic formula is nothing but, so P1 by rho z plus V square by, so V1 square by 2g plus Z1 equals to, so P2 by rho g plus V2 square by 2g plus Z2. Okay, so that is for Bernoulli's equations. Okay, so we are having the constant was that P by rho g plus V square by 2g plus Z equals to constant. So we are measuring from inlet to outlet, then we will get the, so P1 by rho g plus V1 square by 2g plus Z1 equals to, so P2 by rho g plus V2 square by 2g plus Z2. Okay, so this is the Bernoulli's. Okay, so based on this, we are having some gate problems. Okay, so we can go through this. So see here. So while coming to here, so this is the first bit, that is an inverted YouTube manometer. So this is the gate bitmap in 2016. So please see here. So an inverted YouTube manometer is used to measure the pressure differences between the two pipes. Okay, so between the two pipes A and B, as shown in the figure. Pipe A is carrying oil with a specific gravity of 0.8, and the pipe B is carrying water. Okay, the densities of air and water are 1.16 kg per meter cube and 1000 kg per meter cube respectively. Okay, the pressure difference between the pipe A and B is dash kilopascal. Okay, so that means we need to take the pressure value in kilopascals. Okay, so generally we will get in the pressure in newtons. So again, we need to convert that into kilopascals. Okay, and acceleration due to gravity is, so generally we'll take 9.81. So here we are taking it 10 meters per second square. Okay, so please assume here. So here we are having the first limb and here we are having the second limb. That is LHS equals to RHS. So I'll comment here. So this is inverted tube. So that means, so here we need to take the PA minus rho GH. So PA minus rho GH equals to, so PB minus rho GH1, rho GH2, like this. Okay. So see here. So PA, so minus, so here we are having, so two fluids up to here. Okay, that is here oil and here mercury. Okay, and here we are having a single fluid. Okay, so that is the PA minus rho GH1 minus GH2 equals to, so PB minus rho GH. Okay, so here the H is nothing but here, so this is H1, H2, and this is H3, because so here we are considering this one as H1. Okay, this is H1, and here we are having H, that is from B point to here 200 mm. That is here we are having, so that is 200 mm, 100 mm, and 80 mm. Okay, up to here. That is 200, 100, and 80. While coming to here, we are having only 280. Okay, so that means, so PA minus rho GH1. Okay, so minus rho GH2 equals to PB minus rho GH. So H equals to H1 plus H2 plus H3. Okay, so PA minus rho GH1 minus rho GH2. Okay, so here we are having, so rho as 0.8 and the gravitational as 10 and H1 as we are having the value. Okay, and here we are having rho, that is air, G 10 and H2. Okay, here we are having PB, that is pressure at the B point, minus, so density of water. Okay, then G, which is nothing but 10, and here we are having H1, H2, and H3. Okay, that is, so 80, 200, and 100. Okay, by substituting these values, so the first problem. So generally, for example, fluid mechanics, so we'll get minimum, so 1, 2, and maximum 4 bits. Okay, so up to now, so we are seeing only either 2 or 3 bits. Okay, so each question carries 2 marks, or sometimes it will carry, so 1 mark also. So basically, they will give for 2 marks. Okay, so see here. So when coming to the, so next problem, that is oil kinematic viscosity of, that is V oil equals to 1 into 10 to the power of minus 5 meters per second. So they have already given that. So oil kinematic viscosity is, so V oil equals to 1.0 10 to the power of minus 5 meters per second. Okay, so flow through a pipe of 0.5 meters diameter with a velocity of 10 meters per second. That is, we are having a pipe of diameter 0.5 meters with the velocity of 10 meters per second, because the fluid is moving there. Okay, so at the same time, so water is flowing through a model pipe of diameter 20 mm. Okay, in the same way, we are having, so model also. That means we need to go with the prototype, and we are considering this as a model. Okay, that means we are having two types, two pipes. That is prototype pipe and model pipe. Okay, the prototype pipe is for oil, and the model pipe is for water. Okay, so here for satisfying the dynamic similarity, the velocity of water is, okay, That means we need to find out the velocity for the water. Okay. That means we need to find out the velocity for the water. Okay. So please assume here. So prototype we are having the oil and we are having the velocity as 10 meters per second. Okay. And while coming here we have the diameter of 0.5 meters. Okay. At the same time we oil equals to, so there has been the kinematic viscosity, that is so 1.0 10 to the power of minus 5 so meters square per second. So here I am coming to the model, that is for water. We doesn't know the velocity and we have the kinematic viscosity. We are having a kinematic viscosity. Okay. That is 0.89 10 to the power of minus 6 meters square per second and we are having a diameter that's 0.02 meters. Okay. So for this, so we are having the, so right now we need to find out the velocity. Okay. So right now, so we need to find out what are the formulas for velocity. Okay. So we are having the formulas for Q equals to A into V. So with the help of, diameter we can find out area. But here there doesn't be about the discharge. Okay. That means it's just to find out the velocity because we need to find out the velocity. So first of all we need to find out the discharge. Okay. So here discharge is also so unknown. Then what are the other formulas we have? So another formula. So here we are having that Reynolds number formula. Okay. So I'll comment here the Reynolds number formula equals to, so velocity into diameter divided by kinematic viscosity. Okay. So velocity into diameter by kinematic viscosity. Okay. So in that we are having that. Okay. That is, so Reynolds number of oil equals to Reynolds number of water. Okay. Reynolds number of oil equals to Reynolds number of water. So which is nothing but, so V into D by kinematic viscosity equals to, so VD by V. That is, so model with respect to the prototype. Okay. So here we are having V into D. So V has so 10 meters per second and D has so 0.5 meters. That is a prototype. Okay. And so kinematic viscosity equals 1 in 10 to the power of minus 5. So I'll come here again we are having V into W. So that is a, so for model we doesn't know the velocity of the water. So that is VW into 0.02. So divided by 0.89 to the power of minus 6. Okay. So ultimately here we are having the 6 terms, that is V D V V D V. Okay. So here we know the diameter, so both diameters and both kinematic viscosity, one velocity. Okay. And we need to find out the another unknown term, that is velocity of the water. So therefore, with the help of this formula, we can find that VW equals 22.25 this per second. Okay. So like this. Okay. So observe the form very clearly. Okay. So here we are taking the prototype and model. So prototype equals to model. Okay. So Reynolds number for oil equals to Reynolds number of what? That is, so Reynolds number of prototype equals to Reynolds number of model. Okay. And the Reynolds number is VD by V. That is kinematic viscosity. Okay. With the help of this one, we can find out the velocity of water, that is 22.25 meters per second. Okay. So in the same way, so you can say this. So I'll come here. Prod number is the ratio of prod number. So here we have options as buoyancy forces to viscous forces, then inertia forces to viscous forces, then buoyancy forces to inertia forces, then inertia forces to gravity forces. So we can go to the inertia forces to the gravity forces. Okay. So see here. So here we have a match the following for non-dimensional number with the corresponding difference. Okay. So first of all, here we are having Reynolds number, so Grashof number, Nusselt's number, and Prundel's equation. Okay. So Reynolds number, Grashof numbers, so Nusselt's number, and Prundel's equation. Okay. So while coming to here, so we have the options as, so P1, Q3, R2 is, that is, so Reynolds number. So welcome to definitions behind buoyancy forces by viscous forces. Okay. So momentum diffusivity by thermal diffusivity and inertia forces by viscous forces and the convective heat transfer by conduction of heat transfer. Okay. So listen. So first of all, so we know that Reynolds number. So Reynolds number formula is nothing but inertial forces by viscous. That is P equals to 3. Okay. P equals to 3. So here P equals to 3 means either the answer should be B or answer should be C. Okay. And the next thing. So Grashof number. Okay. So Grashof number is nothing but so buoyancy forces divided by viscous forces. Okay. Buoyancy forces divided by viscous forces. And Q is nothing but 1. Okay. So that means here we are having. Okay. That is it is from B or P. Okay. Then Nusselt number. Okay. Here we are having that Nusselt number. So Nusselt number is nothing but so convective heat transfer divided by conduction heat transfer. Okay. Convective heat transfer by the conduction heat transfer. Okay. Done. So frontal number is nothing but the momentum diffused divided by thermal diffused. Okay. So that means we'll come to here. Here we are having the answer as D. Okay. So like this. Okay. So here also we are having that for an ideal gas. Sorry. So for an ideal gas, the value of Joule-Thomson coefficient is. So for an ideal gas, the value of Joule-Thomson coefficient is. So we are having the options as positive, negative, 0, and indeterminate. Okay. So we are having that positive, negative, 0, indeterminate. Okay. And the answer is for an ideal gas, the value of a Joule-Thomson coefficient is 0. Okay. It is 0. Okay. So like this. Okay. So listen. So in this one we are having only one bit. That is the floating body. The buoyant forces act as the okay for a floating body. So actually, so for floating bodies name so we will get the boundary layer theory. Okay, in that we can find out the floating bodies and the buoyancy forces. Okay, so here we have the for a floating body. So the buoyant forces act as the so we have the options of center of the floating body, the center of gravity, then center of the fluid vertically below the body, then center of the displaced fluid. Okay, so here we are having the so for a floating body, so the buoyant forces act as the center of the displaced fluid. That is our option is D. Okay, our option is D. Okay, so see this paper. Okay, here. So repeated bit came. Okay, so Grashof number signifies the ratio of. Okay, so Grashof number signifies the ratio of. Okay, so in this question, so already we got this one. Okay, okay, so like this. Okay, so here we are having so Grashof number signifies the ratio of okay buoyant forces to the viscous forces like this. Okay, here already we have okay that is buoyancy forces. So it is the ratio of buoyancy forces to the viscous forces. Okay, so like this. So they will have so different types of. So here are steady one-dimensional heat conduction flow. So it will belong to the heat transfers. So like this. So we are having so different types of okay. So different types of bits. Okay. So minimum of one bit will come and the maximum of so 4. Okay. So listen. So again I'm showing this one. Okay. So here also we are having the critical path method. So the cause time slope of an activity is given by. Okay. The fraud number is the ratio of. Okay. Then so like this here we have some tables. Okay. So here the velocity field in an incompressible flow in a Cartesian system represented. So this is vector potential that is V equals to 2 of x square minus y square with respect to I plus Vj plus Vk. Okay. So here we are finding that I equals to T, then U equals to J and such that is singular and time t equals 3, like this. So here we have the valid expression. Okay. So I'll come to here, we have hand answers. So 4xz minus 6x. Okay. So here we have for an ideal gas, the value of Joule Thomson coefficient is 0. Okay. So this is from IIT Madras. Okay. So here we are having that. So which are the following true with the so so then so the okay. So what are the correct? Okay. So like this they will ask. Okay. So you can see clearly. So here they are asked that if for a floating body the band forces acts as the centroid of the displaced fluid. Centroid of the displaced fluid. Okay. So I'll comment here. So only one bit has come. That is Grashof number signifies the ratio of buoyancy forces to the viscous forces. So here, okay, so the strength materials. So coming to here, we are having an inverted U2, so it's already solved problem. Okay, and this also has explained. So while coming to here, a steady laminar boundary layer is formed over a flat plate. Okay, that means a steady laminar and a boundary layer. A steady laminar boundary layer is formed over a flat plate. Okay, the free stream velocity of the fluid is u naught. Okay, the velocity profile at the inlet AB is uniform. Okay, that means while coming to here, we are having that A and B is uniform. Okay, the velocity profile is uniform. Okay, that is it is an unit quantity. Okay, so while the downstream location CD is given by, okay, so here the CD is given by U. U equals to U naught of 2 y by del minus y by del whole square. That is, here A and B is constant and C and D are not constant. Because, so while coming to C, so A and B are the single line, and so here we are having the velocity constant is also so in equal profiles. So I'll come to here, it starts from 0 and it emits some values. Okay, and this is the profile of del. Okay, so here the ratio of the mass flow rate, okay, so it's leaving through the horizontal section B and D. Okay, so here we are having that so mass flow rate is leaving through with the B and D, that is with this one. Okay, so section BD that entering through the vertical section A and B. Okay, so and it is entering through the vertical section A and B. So they will give so different types of these. Okay, so we are having the formula as, so here the basic formula is, so integral of flow with respect to V bar n with respect to dA equals to 0. Okay, so here we are having the steady process. So they are as the steady process. Okay, so welcome to here we are having, so here, so B, A, C, D, B. Okay, that means so if we assume this is a rectangle, if we need to close it means, so AB, CD, DC, CA. That is A to B, B to D, D to C, C to A. A, B, D, C, A. Okay. So, but according to this condition, we are considering from, so B, A, C, D, B. Okay. That is B, A, C, D, B. Okay. So, so this is the constant volume because the constant volume doesn't changes. Okay. Welcome to here. We are having the integral of Ts with respect to the density with the V and N. Okay. dA equals to 0. Okay. So here we are having that CS is nothing but the controlling of the surfaces and N is nothing but the unit vector perpendicular to area. Okay. So while coming to here, CS stands for the control. Okay. So control of the surfaces. Okay. Done. So here we are having that fluid. So we are going to take the incompressible fluid. So for that one, so the density is constant because we are having compressible fluid and incompressible fluid. For incompressible fluid only, so we are taking the density equals to constant. Okay, where the density is constant, there the fluid is nothing but the incompressible fluid. So we are having two types of fluid, that is compressible and incompressible. So here, so they are dealing with incompressible fluid because where the density equals to constant. Okay, so here we are having the velocity that. So we are using the same formula. Okay, that is rho. So that is integral of. Okay, here we are having integral. So integral of rho. Okay, so integral of rho. So integral of rho equals to v into n equals to dA equals to 0. Okay, that is so rho into integral. So we are taking the limits as a and b because we are taking the first condition, that is a and b vn to dA plus rho into integral of v into del with respect to vn dA plus rho into integral of dc. Okay, and dv. Okay, so we are concentrating on each one and we are taking that. So this one. Okay, and so we are having so rho integral 0 to del minus u naught b into dy plus rho into integral a to del. So because there v equals 0. Okay, and here also we are taking that. So instead of this one, so they have given the formula that u equals to u naught into 2 into so y minus del minus y minus del square. Okay, so like this, so we'll get the answer 0.33. Okay, so in this model we need to solve the problems. Okay, so this is a 2016 paper. Okay, so like this we are having the different models. Okay, so here generally they ask for the inverted models, not only in inverted conditions, so they ask on the regular process also. Okay, so and again we are having so different types of papers also. Okay, so one second. Okay, so if anybody needs the PPTs means you can share your mail ID to me. Okay, so I'll forward to you. Okay, so please go through with the chat box and so please enter your mail IDs. Okay, so I'll send the. Is there any doubts? You can ask me. Yeah. So wait for a minute. I will share the feedback from your attendance.